This is the first video of complex numbers, and in this video I have two main topics that I'll cover. The first is we'll define what a complex number is, and then I'll show you how to do some simple arithmetic operations on complex numbers. And you can read more about this in Greenberg on pages 1108 to 1113. And we'll first use complex numbers in Cartesian form, which is written as z, being a complex number, is equal to x plus I, y. The second topic will be how to operate or defining what exponents of complex numbers are, and related to that are trigonometric and hyperbolic functions. And that's in pages 1115 to 1120 of Greenberg. And an exponent of a complex number, for example, is e to the z, or that's the same thing as e to the x plus I, y. What I'd like you to take away from this video, as well as the exercises in the homework, you'll know what a complex number is, and you'll also know how to do some simple arithmetic operations, as well as use exponents of complex numbers. Now, in middle school, when you started learning algebra, you learned how to solve an equation of the following form. So x minus b equals 0, and using algebra you learned that x is equal to b. And if b is a positive number, then we knew that x is also a positive number. And about the same time, you learned about negative numbers, so that you can solve equations of this form. Right? So this gives x is equal to minus b. So we learned that numbers have on the positive axis as well as on the negative axis. You also learned, when dealing with powers, for example, x squared minus b is equal to 0. You learned that this equation could be solved by taking the square root of b, for example. So x is equal to plus and minus the square root of b. So we learned about taking the square root or the nth root of numbers to solve these sorts of equations. So finally, getting to complex numbers, we need complex numbers to solve equations such as x squared plus b is equal to 0. And so that means x is equal to the square root of minus 1 times the square root of b, and the square root of minus 1 is defined as I, or I is defined as the square root of minus 1. So the triple bars here means a definition. Okay, so this is sort of a build-up to the different types of numbers we use. Again, numbers on the positive axis, the negative axis, and finally numbers on the complex plane. So a general complex number is written as, for example, z is equal to x plus I y. So in this equation, x is the real part of z, that is, we would say that the real RE, the real part of z, is equal to x, and y is called the imaginary part. So we have a real part and an imaginary part. You shouldn't read into the meaning, the sort of conventional meanings of real and imaginary. These are just words that are used to describe these different parts of the complex numbers. So the imaginary part is no less true or real than the real part, so to speak. So the imaginary part is, we would denote that as capital IM of z, and that's equal to y. It's the part that's multiplied by the imaginary, or by I, the square root of -1. Also, I'd like to note that the plus sign does not mean addition. Rather, it means that the the imaginary number is a combination of the real and imaginary part. So to make the number complete, it has both, again, the real and imaginary part. We can plot z. So because z has both a real and imaginary part, to represent z in a plot, we need two axes. And those two axes make up what is called as the complex plane. So we could sketch, so the horizontal axis, x, is often used for the real part. It's the real axis, whereas the vertical axis is used for the imaginary part. So x plus iy has an x value of x and a y value of y, and z would be noted by this point. Z is equal to x plus iy. And you'll see that we'll talk about this later, but we can describe this this coordinate also in terms of polar coordinates, where it has an angle theta from the real axis, and it has a length of r from the origin. And also, I should note, I'd like to define the modulus of z, which is equal, it's real, it's equal to the square root of x squared plus y squared, and that's equal to r, the length of r, well, the length of this arm, and that's r. And so the modulus is a real number. Okay, so that does it for some basic definitions of a complex number. Now let's talk about some simple arithmetic. So let's start with addition and multiplication. And those operations are done just like you do with real numbers, but for the solution, you give, well, the solution is given in terms of the real and imaginary parts separated. Okay, so for example, let's consider the sum of z1 plus z2, and using our original description of a complex number. This is our Cartesian description. We have x1 plus I y1 for z1, and then we're going to add z2, which is x2 plus I y2, and that's simply equal to x1 plus x2, that's the real part, plus the imaginary part is I times y1 plus y2.
Okay, so with multiplication, we will multiply z1 times z2. And again, z1 was x1 plus I y1. And z2 was x2 plus I y2. And we just multiply this out as we did before in algebra. So we get an x1 and an x2 for the first two terms. And we'll multiply x1 times I y2. And then we'll multiply an I y1 times x2. And then finally, we multiply an I squared, I times y1, y2. So remember that I is the square root of minus 1. So when we square I, we get a minus 1. And so we're going to collect terms, and we're going to collect real terms first. So the first real term is x1, x2. The second real term is this minus 1 times y1, y2. And then we have two imaginary terms. We have an I times an x1, y2 plus x2 times a y1. And this would be the product of two imaginary numbers. Now I'd like to define the complex conjugate. the complex conjugate of z is denoted z with a bar, and it's the same as z, but with the imaginary part multiplied by -1. So it's the real part of z plus the imaginary part times -1. I guess, yeah, so it's the imaginary part times -1. So, for example, if z is equal to 3 plus 2i, z bar is the real part of z, which is 3, plus the imaginary part multiplied by -1. So in general, if z is equal to x1 plus iy1, then z bar would be x1 minus iy1. Sorry, I guess I don't need the subscripts if I'm just using a general z here. So one quality of the complex conjugate is if we multiply the complex conjugate and z, if we take the product of z and its complex conjugate, we get a real number, and that real number is x squared plus y squared. It's the square of the modulus. And I'd like you to stop the video and verify that this is what you get when you multiply z and its complex conjugate. So please go ahead and do that. Okay, so that was multiplication. Now let's consider division. So let's divide z1 by z2. So the trick is, we know how to multiply two imaginary numbers, but we don't know how to divide by an imaginary number. There's no real definition for that. So what we're going to do is we're going to do a little trick here. We're going to multiply z1 and z2 by 1. We're going to multiply by 1, and that 1 will be the complex conjugate of z2, the complex conjugate of the denominator in the numerator, and it's complex conjugate of the denominator over itself. And when we do this, we get x1 plus iy1, that's z1, times x2 plus iy2, that's z2, except for we're multiplying by its complex conjugate, so we got to put a minus there. That's the numerator. And then the denominator is x2 plus iy2 times x2 minus iy2. And so when we evaluate the numerator, we get an x1 times an x2 minus an x1 times an iy2 plus an iy1 x2. And then we have a minus I squared, which becomes, I'll go ahead and write it, minus I squared times a y1, y2. And since we have an I squared, this becomes a -1, and then we have a -1 in front of it. So this becomes a plus 1. And then the denominator becomes x2 squared plus y2 squared. It's the square of the modulus again. So we write the final form of the quotient in terms of collecting all the real parts. So that's x1, x2 plus y1, y2 all over the denominator. And then we collect all the imaginary parts, and that gives us an x2 y or y1 y2, y1 x2, and then an x1 y2. This looks like I wrote an I there. This should be a x1, y2 all over the same denominator. And so there you have it. So now let's look at exponentials. Exponentials of imaginary numbers. So if we raise e to the z power, where z is the general imaginary number, that's the same as raising it to the x plus I y power. And we can apply what we know about products of exponents. And we know that that's e to the x times e to the iy power. So we're all good with this. This is something we know how to deal with because it's a real number, but we don't yet know how to deal with e to the iy power. So to gain some insight on what e to the iy power is, let's take the Taylor series expansion of e to the iy evaluated at y is equal to a, and we'll set a equal to 0. So I pasted the Taylor series formula just to remind us how to do this. So we expand e to the iy, again about 0. And so the first term is the function itself. So that's e to the iy, which is 0. And so this will turn into a 1. And then we have the first derivative of e to the y0. And so that becomes, well, e to the u is just, the derivative of e to the u is just e to the u. And then we have to take the derivative of u with respect to y, and that gives an I. So that gives e to the I0. And then we have to multiply that by y minus 0. And then so that's the first derivative term. And then the second derivative term is we have to take the derivative of I e to the iy, and that becomes an I squared e to the I0 times y minus 0 squared all over 2 factorial. And then if we continue to do this, go ahead and take another third derivative. So that's an I times an I squared, so that's an I cubed over 3 factorial e to the I0 times y minus 0 cubed plus higher order terms. So I've just drawn out 3 terms, but I'm going to try to show you all the terms. So if we just look at the real parts, we get a 1 here. This part stays imaginary, but this part is real because we have an I squared. This becomes a minus 1 here. So we get a minus, this is a 1. We get a y squared over 2 factorial. And then it turns out if we continue to look at higher terms, we get a plus y to the 4th over 4 factorial minus y to the 6th over 6 factorial, and so on. So that's the real part. So the real parts came from this. Oops. And so forth. And then we have the imaginary part. The first imaginary term is this term. And that gives us an I times, again, this is a 1, and we just have a y. And then the next term is this is I squared is minus 1 times another I gives a minus I over 3 factorial. Again, this is a 1, and this becomes a y cubed. And if we were to continue to do this, we would get a y to the 5th. Oh, I'm sorry, the I is already out there, so I don't have to write it again. And we get a 5 factorial plus and so forth. So the real parts have the even powers of y. The imaginary parts have the odd powers of y, and it turns out that this is equal to cosine y. This is the Taylor series expansion of cosine y, and this is the Taylor series expansion of sine y. So from this, we see that e to the iy is equal to cosine y plus I sine y. And this is Euler's equation. Or I guess it's Euler's formula. And this is a formula we're gonna use a fair amount, so please keep that handy to remember. So back to our problem of defining e to the z. That's e to the x times e to the iy, which we can write in terms of Euler using Euler's formula. Okay, so using Euler's formula, given that e to the iy is a sum of cosines and sines, we can solve for cosine or sine in terms of e to the iy, and it turns out that cosine y is equal e to the iy plus e to the minus iy over 2, and sine y is equal to e to the iy minus e to the minus iy over 2. And likewise, we can describe z in the same way. To express cosine z and sine z in terms of exponentials. And you might recall, we looked at this before for hyperbolic functions. We saw that, for example, the hyperbolic cosine of a number, in this case, we'll use the general imaginary number, that's equal to e to the z plus e to the minus z over 2. And the hyperbolic sine of z is equal to e to the z minus e to the minus z over 2. So I hope you'll see that these two relations are rather similar between the sine and hyperbolic functions. So I'd just like to point out that similarity. Okay, well, that should do it for this video. We'll catch you on the next one.